Hey everyone, and welcome back to the podcast. I'm Mark, and as always, I'm joined by the ever-inquisitive Jenny.
Hello, Mark. Always a pleasure to be here, diving into the fascinating world of tech. Today we've got a topic that's, it's kind of a big deal for the future of computing.
It really is. We're talking about SRAM, Static Random Access Memory, the unsung hero, or maybe I should say, the increasingly stressed times hero of pretty much every processor out there.
Increasingly stressed? That sounds ominous. What's happening with our trusty SRAM?
Well, it's all about scaling, or rather, the lack times of scaling. See, for decades, we've been shrinking transistors, making them smaller and faster, packing more and more onto a chip, SRAM, which is used for cache memory. That super fast memory that your CPU uses constantly has been shrinking along with everything else.
Okay, I'm with you. Smaller transistors, faster chips, more memory. That's Moore's law, right?
Exactly. But here's the thing. SRAM is hitting a wall. We're getting down to these incredibly tiny process nodes, like 3 nanometers. And SRAM just isn't shrinking at the same rate anymore. It's like it's saying, I'm done. I can't get any smaller.
Wow, so what's causing that? Is it a physics problem?
It is. It's a combination of factors, really. We're using these FinFET transistors. They're 3D structures, which have been great for scaling. But they're getting so small that we're running into quantum effects and increased variability. Basically, it's getting harder and harder to control the behavior of electrons at that scale.
So each tiny transistor is becoming less predictable?
Precisely. And with SRAM, you need those transistors to be incredibly reliable. SRAM cells, the basic building blocks of SRAM, typically use 6 transistors. If even one of those is slightly off, the whole cell can fail. So, as variability increases, it becomes harder to make reliable SRAM.
That makes sense. So what's the impact of all this? Are our chips just going to get bigger?
That's one of the main consequences. If SRAM isn't shrinking, but we still need more cache memory for performance, then the cache portion of the chip has to get bigger. And a bigger chip means it's more expensive to manufacture. We're seeing this already with some of the latest processors.
So it's hitting our wallets, basically?
Indirectly, yes. More expensive chips mean potentially more expensive devices. But it's also impacting performance. Chip designers are having to make tough choices about how much cache to include, and that can affect how fast a processor can run.
Okay, so what are the solutions? Are we stuck with these giant, expensive chips?
Not necessarily. There are a few different approaches being explored. One is architectural. Companies like AMD are using something called 3D V-cache, where they stack layers of SRAM on top of each other. It's like building a skyscraper instead of a sprawling suburb.
That's a clever analogy. So you get more memory without increasing the footprint of the chip?
Right. And Intel is working on multi-chiplet designs, where they break up the processor into smaller, independent chiplets that can be connected together. This allows them to use different manufacturing processes for different parts of the chip, potentially optimizing for cost and performance.
So it's like a modular approach to chip design?
Exactly. But these approaches also add complexity. Connecting all these chiplets or layers introduces new challenges in terms of communication and power consumption.
So it's not a perfect solution, but it's a way to keep pushing forward?
Precisely. And then there's the really exciting stuff, the emerging memory technologies. We're talking about things like MRAM, magnetoresistive RAM, and FRAM, ferroelectric RAM.
Those sound like something out of a science fiction movie.
They kind of are. MRAM, for example, uses magnetic states to store data instead of electrical charge. This could potentially be much more scalable and use less power than SRAM.
That sounds incredible. Are these technologies ready to go?
Not quite yet. They still face challenges in terms of manufacturing and integration. MRAM, for instance, can be slower than SRAM and more expensive to produce. But the research is ongoing, and there's a lot of potential there.
So it's a race between improving existing techniques and developing these futuristic new memories?
That's a great way to put it. And it's not just about performance. It's also about power consumption. As we move towards more and more mobile devices and data centers, reducing energy usage is becoming increasingly critical.
Right, because smaller devices and massive data centers both have huge power constraints.
Exactly. And some of these new memory technologies, like MRAM, have the potential to be much more energy efficient than SRAM.
It's like a whole new frontier in memory technology is opening up, driven by the limitations of what we have now.
Precisely. And it has implications for everything from the phone in your pocket to the giant AI models that are powering the next generation of applications.
What about the long-term view? Are we going to see a complete shift away from SRAM?
That's hard to say. SRAM is still incredibly fast, and it's deeply embedded in our current technology. It's more likely that we'll see a hybrid approach, where different types of memory are used for different purposes, depending on their strengths and weaknesses.
So a bit of SRAM, a bit of MRAM, maybe some FRAM thrown in for good measure?
Possibly. It's going to be a fascinating evolution to watch. And the ethical considerations are important too. As these technologies become more complex and expensive, how do we ensure equitable access?
That's a great point. It's not just about making things faster and smaller. It's about making sure the benefits of technology are available to everyone.
And we also have to think about the environmental impact. Manufacturing these advanced chips requires a lot of energy and resources. So, finding ways to make the process more sustainable is crucial.
It's a complex web of technological, economic, and ethical considerations. It seems there are as many challenges as opportunities.
Absolutely. But that's what makes it so exciting. We're at a turning point in how we build computers, and the next few years are going to be incredibly interesting.
Well, Mark, as always, you've given us a ton to think about. Thanks for breaking down this complex topic in such an engaging way.
My pleasure, Jenny. And thanks to all of you for listening. Join us next time as we continue to explore the ever-evolving world of technology.